Okay, so this is the example of the colliding disks. And I'll read the problem so that everybody can be reminded of it. It said, in an assembly line, a large uniform disk rotates counterclockwise when viewed from above with angular speed omega big D equal to 1 radian per second, about an axis through its center of mass and perpendicular to the flat surface of the disk. And we were given a picture, kind of a perspective view. There's the disk. There's the axis going through the center and perpendicular to the flat surface of the disk. And this thing is rotating counterclockwise with an angular speed omega big D of 1 radian per second, like so. And it's got a radius, I'll denote it down here, capital R, according to the picture. Oh, I got 2 more people to admit. Okay, now, there's a second uniform disk with the same mass as this first one, but half the radius. And it's rotating clockwise when viewed from above.
Sorry.
With angular speed omega little d equal to 3 radians per second, about an axis through its center of mass and perpendicular to the flat surface of the disk. Let me try to draw that one next. It, by the way, initially, this second disk is suspended just above the first disk, with the center of the second disk displaced from the center of the first disk by an amount equal to half the radius of the first disk. So the second disk has half the radius of the first, rotating about an axis through its center, like that, rotating clockwise with an angular speed omega little d of 3 radians per second. It's just suspended right above the first disk by some device that I don't care what that is. It's just holding it up there. Okay, that's the initial picture. Then, suddenly, the second disk is allowed to fall onto the first disk, and the 2 disks undergo a completely inelastic collision. This is a rotational version of the completely inelastic collisions we studied in chapter 9, where 2 objects were moving along linear motion, then collided and stuck together and moved as one thing. Same thing's happening here, except it's with rotation. Okay, so there's complicated stuff going on, but after the collision, the second disk just falls straight down. Boom, onto the first one. Okay, and ends up riding on top of the first one, and we've had a completely inelastic collision. And we want to know the angular velocity they have afterwards. So if this is the initial picture, kind of from a side view, I could also draw that initial picture as a top view. That might be helpful, in which there's the big disk rotating counterclockwise about its axis through the center, and the little disk is rotating and suspended just above the first disk and rotating, excuse me, got that arrow wrong on that one, counterclockwise for the big one and clockwise for the little one. All right, that's initial. Final. All right, the collision itself may be complicated and messy, but what we end up with is the second one, the smaller one, riding on top of the first one. So my picture is going to look very similar to the top view I just drew. Okay. Like that, except now there's just this one axis right through the center of the big one, and they're both rotating about that. But I don't know whether the whole thing is rotating that way or that way. And I want to find that angular velocity. Because the second one is now just riding on top of. The second smaller one is riding on top of the bigger one. Okay, so because I have a collision, but with rotation, we're going to use conservation of angular momentum. I'm going to take the z-axis to be coming straight out of the screen towards us. So LZ1 must equal LZ2, or LZ initial must equal LZ final, if you want to write it that way, where LZ1 refers to the angular momentum about the z-axis before the collision, and LZ2 is the angular momentum after the collision. And then I'm going to write down symbolic expressions for those angular momentum values. So let's come down here now. Oh, let's deal with before the collision first. So that's this picture here, or this one, before the collision. And I just have two disks, each rotating about an axis through its center. So the formula we would want to use for LZ1, when you have an extended body rotating about an axis, the formula for the angular momentum is the rotational inertia about that axis, I, times the angular velocity, omega. So for the big disk, I'll call the rotational inertia I big D, and then I'll multiply by the angular velocity, which I'll denote that way. It's positive because counterclockwise is positive. And then the little disk is rotating initially clockwise. That's going to give me a negative contribution to the angular momentum. And so then I need the angular momentum of the little disk about its center times omega little d, where those omega values are up here, there and there. Now, for the I's, the rotational inertia, well, we have uniform disk with an axis through its center and perpendicular to the flat surface. So that's one of those special cases where you can just look up the rotational inertia in that table in chapter 10. For a disk with the axis through the center and perpendicular to the flat surface, the rotational inertia is 1/2 times the mass times the radius squared. So that's what I would write symbolically for I big D. Now I little d, rotational inertia for the axis through the center of the smaller disk, well, it's still a disk. So 1/2 mass, I'm told the two disks have the same mass, times the radius squared. Now the little disk's radius is big R over 2. So I need big R over 2 squared. So what is this? That's m times r squared. 2 squared is 4. 4 times 2 is 8. Looks like that's m r squared over 8. All right, so when it comes time to work with LZ1, I'll put this expression in for I big D and this expression in for I little d. And I know omega big D and I know omega little d. So that's about as much as I need to say right now about LZ1, the initial angular momentum. Now let's talk about LZ2. Okay, that's with the final picture where both disks are rotating about this one axis right there, which is the center of the big disk. Okay, so for LZ2, they both have the same angular velocity, but there will be the angular momentum of the big disk. That's still I big D, same expression, plus the rotational inertia, I should say, of the big disk, I big D, and then plus the rotational inertia of the little disk. Now here I have to be careful because the little disk is now rotating about that axis at the center of the big disk, which means the little disk is no longer rotating about an axis through its center of mass. It's rotating about an axis displaced over to the edge of the little disk. So I have to use the parallel axis theorem. But let me just call that rotational inertia for now I little d prime, meaning it's going to be some slightly different expression for rotational inertia compared to the initial situation. And then I multiply that, that's the total rotational inertia by the final angular velocity, omega. I called it omega 2. You can call it omega final or whatever is reasonable. Okay, now, what do we need to say about that ID prime? Rotational inertia of the little disk about the axis through that point at its edge. I have to use the parallel axis theorem. So that's the rotational inertia that I would have had if the axis were through the little disk's center of mass. That would be that expression, I little d, plus what your book calls mh squared in the parallel axis theorem, where m is the mass of the thing that's rotating, in this case m, and h is the distance between the axis that would go through the center of mass, that's what I just drew there, and the actual axis, which is the black dot. And the distance between those two axes is half of big R. So big R over 2 squared is added on like that. So let's see what that gives us here for ID prime. So ID is mr squared over 8. We already figured that out. And so I'm adding to that mr squared over 4. And we can add those two, mr squared over 8 plus mr squared over 4. You factor the mr squared, you're just adding 1/8 plus 1/4. 1/4 is 2/8. 2/8 plus 1/8 is 3/8. So this is 3 mr squared over 8. We've changed the rotational inertia for the little disk. Okay, so let's put the LZ1 expression equal to LZ2. All right, so here we go. I big D times omega big D, positive contribution. Then there's a negative contribution, so minus I little d omega little d, that's LZ1. And that must equal LZ2, which is I big D mr squared over 2 plus I little d prime 3 mr squared over 8, all times omega 2. All right. Now let's start, let's continue here with this. All right, now we know what I big D is. We already said mr squared over 2. I little d is mr squared over 8. So actually on the left, I can factor an mr squared over 2 on the left. And what I'll have I'll have some square brackets here, and what I'll have inside the square bracket is omega big D minus omega little d over 4. Close square bracket. I just factored an mr squared over 2 on the left. And now I'm going to factor an mr squared over 2 on the right. Square brackets again. So then we'll have 1 plus 3/4, all times omega 2. mr squared over 2 on both sides will cancel. And of course, 1 plus 3/4 is 7/4. So 7/4 omega 2. And my job was to find omega 2. So multiply both sides by 4/7. You get 4/7 times omega big D minus omega little d over 4. And I did, you wouldn't have to do this, but I went ahead and took that 4 out front up in the numerator and distribute it through the brackets. And I got then inside the brackets 4 times omega big D minus 1. It's about as pretty as I can make that answer look. And that's when I plug in numbers. Excuse me, not minus 1, minus omega little d. Then I plug in numbers. Omega big D is 1 radian per second. And omega little d is 3 radians per second. And this answer, because of the algebra being done carefully, is going to give me the magnitude and the direction of the rotation. Because the sign of this answer will tell me if the rotation of this compound object after the collision is counterclockwise or clockwise. The positive value for omega 2 corresponds to positive omega, counterclockwise rotation, and a negative value for omega 2 is clockwise. And when you put these numbers in, you get a positive result for omega 2, 0.143 radian per second. And so the positive result tells me that I have counterclockwise rotation. And so that, yes, that was an example problem we did in class in which we had a collision of rotating objects. Okay. And of course, you had a number of Wiley plus homework problems in chapter 11, where you had situations where there were collisions that involved rotation. And so there, basically, the idea is if you have a collision involving things rotating, you use conservation of angular momentum.
Thank you.
You're welcome. Another question.
Can we review moment arms?
I'm sorry, I didn't quite hear that.
Review moment arms.
Moment arms. Okay. Review of moment arms. So that concept of a moment arm first appeared for us in chapter 10, which was our first chapter on rotation. And in chapter 10, we had rotating bodies, rigid bodies rotating about a fixed axis of rotation. And what we talked about there was when you have a rigid body that can rotate about a fixed axis, the way you get it to rotate is you apply a force somewhere. And if that force has what's called a moment arm, you will get what's called a torque. And it's the torque that causes the object to rotate. So we need to be really clear on how to calculate torque. And in chapter, and there were kind of two ways. We introduced a way to do it in chapter 10, and then we introduced a somewhat different way in chapter 11. The moment arm approach was mainly in chapter 10, although you can use it in chapter 11. And so what we tended to do is we tended to give you an object. It really didn't matter what shape it was, but it was going to be some rigid object that could rotate about an axis. So let me draw something. Let's just say it's shaped like a kind of a lima beam, like that. And you're looking down on it from above, and we've passed an axis of rotation perpendicular to the screen, going through the lima bean there at that one point. And it can rotate in a horizontal plane. Maybe it's sitting right above a table. It's lying on a table with the axis coming straight out towards us. All right, now if I come along and at a certain place, it could be on the edge, it could be somewhere else, it could be like right there. I apply a force right there. Now I need to tell you how big that force is, the magnitude in newtons, and in what direction. Maybe I pull that way with a force, F, okay? Like I said, I gotta tell you the magnitude of that force, and I gotta tell you something about the direction. My contention is that if that's the only force in this horizontal plane, and there's an axis of rotation like that, this object will rotate about that axis. And in fact, I can just look at it and I can visualize how it will rotate, given that axis where it is, given the force that I applied where it is and the direction of it. I know that the lima bean would rotate as I look at it counterclockwise from above. That's going to be important. And I want to be able to figure out what's called the torque due to that force F, because it's the torque that will cause the thing to rotate. All right. Symbol for torque, lowercase Greek letter tau. In addition to the force vector F that I've drawn there, you need to know one other thing, the position vector. That's the arrow from the axis out to the point where the force is acting. Boom, like that. R arrow, okay? That's also a part of your picture. Okay, so how do we calculate the torque tau due to that force F in that situation? First of all, torque is a vector, so I gotta leave space for a way to designate the direction of it. And then I will multiply by the magnitude of that force that's causing the torque and this quantity called the moment arm for the force. And your book denotes that R sub perpendicular. And that's called the moment arm of the force. Two things then are equally important in calculating torque in a scenario like this. Neither is more important than the other. The magnitude of the applied force and the size of the moment arm. And they just get multiplied together. And then the box out front is for the direction of the torque. And in chapter 10, where the rotation was about a fixed axis, like this lima bean, about the axis that you see, you only have two choices for the rotation, counterclockwise or clockwise. That's why I said I had to be able to visualize this and see which way it would rotate, and it would rotate counterclockwise. And the sign convention is counterclockwise rotation is a positive torque, and clockwise rotation is a negative torque. And the picture I drew is a force that would cause counterclockwise rotation. So I put a plus sign in that box, and that denotes the direction of the torque, at least as far as chapter 10 is concerned. Now, what's really important then, in addition to also knowing the size of the force, F magnitude, is how big is this quantity called the moment arm? Because we have to be able to calculate that in a picture like you're given here. All right, so now let me talk about that. How do you find the moment arm? It's basically a two-step process, starting with the picture you've got right here. Now, first, take the force itself, the force vector, the green arrow in my drawing, and extend the line of that force. I draw it with a dashed line. Either way, above and below the force. That extension of the line of the force is called the line of action of the force. You have to draw that if you're going to get the moment arm right. Because now, here we go. Here comes the moment arm. R perp, R perpendicular. It is the moment arm, the perpendicular distance from axis of rotation to line of action. So you have to be able to draw a line from the axis to the line of action that intercepts the line of action at a 90-degree angle. At least you have to be able to sketch it. And if I try to sketch that, it's going to look something like that. And I'll emphasize that by drawing the little right angle symbol. And it's the length of that red line that is the moment arm. R perp. That is the other key quantity. You have to know the magnitude of that force and the length of that moment arm. Now, the problem has to tell you enough information to get those two numbers, F magnitude and R perp. The thing that makes these kinds of problems potentially confusing is that there are so many variations on ways they can give you that information. But it still boils down to the fact that they have to give you enough information so that you can calculate or you can determine F magnitude and R perp. Okay? Now, they might very well just tell you the magnitude of the force. They might just say, a 5-Newton force is applied to a lima beam in the direction shown in the picture. Now you know F magnitude's 5 newtons. All right, let's talk a little bit about how they might tell you R perp. I suppose if you were really lucky, they would just tell you R perp, but you're probably not going to be that lucky. Probably what you're going to be told is this distance right here. Notice that that would be the magnitude of R vector. That would be that distance, okay? And then they're going to tell you some way to get an angle. Some way boiled down to get, say, that angle right there, phi. And they might do it a number of ways. A lot of times your book likes to do this. Extend the R and tell you that angle up there. That angle is 15 degrees, for example. They might do that. That's an example of one thing that you might see. Then you just have to realize from geometry that if that angle is 15 degrees, so is that phi right there. Then you have enough information. If you know the magnitude of R and the angle phi, then look at that right triangle below. R perp is magnitude R times sine phi. Okay? So you just got to get that number R perp correctly and multiply R perp by F magnitude and figure out whether it's counterclockwise rotation or clockwise. And if you can do that, no matter what kind of picture we throw at you, then you fully understand torques as far as chapter 10 is concerned. Anybody want to ask me any questions about anything I've said on that? No, okay. Okay, so the question was to talk about moment arms, so I'm guessing that that's what you wanted. Now I have a request in the chat box to review chapter 15. Okay, that's a lot. So why don't we narrow that down a bit? There were three main things in chapter 15. Studying what's called simple harmonic motion, starting with a horizontal block and spring. Okay, where there'd be some equilibrium situation where the block would rest. Block is connected to the spring. The other end of the spring is connected to a fixed wall. And then somehow you get that block spring system oscillating on the horizontal frictionless x-axis. And we basically want you to be able to tell us anything whatsoever about that oscillatory motion. That's one big idea in chapter 15. Another big idea in chapter 15 was the fact that if you have a system like a block and a spring, moving with simple harmonic motion, and you pick the system to be the block plus the spring. The only force doing any work there is the spring force. Therefore, the system's mechanical energy is conserved. So you can go back to chapter 8 concept of conservation of mechanical energy to study simple harmonic motion of a block and a spring. And that opens up a whole new calculational method, conservation of mechanical energy, which is very, very powerful. And there are whole hosts of homework problems where you have to apply conservation of mechanical energy. And then we had a third idea, pendulums, both the simple type and the physical type, starting with the case of a pendulum where its restoring torque comes from gravity. So that's like something that would normally, like this pencil that would hang vertically. This would be a physical pendulum in equilibrium. And if I displace it from equilibrium and let go, it would oscillate back and forth. Now, it's too much friction between my fingers to get much oscillation here, okay? But that would be a physical pendulum. But it is simple harmonic motion if the angle, theta, between the pendulum and the vertical is small, which means small compared to 1 radian. So we studied pendulums, the simple kind, where all the mass is assumed at the end, and the physical kind, where the mass is distributed along the length. Okay, now we've narrowed down the question. Okay, wait a minute, then there's a jump to chapter 17. Let's do one thing at a time. Chapter 15, the connection between U and V. We didn't use the U notation in chapter 15. The U notation showed up in chapter 16. I understand how that can cause confusion, but I think maybe you're asking about chapter 16 then. I'm thinking maybe that's what you're asking about, chapter 16, where we studied, yeah, okay, good. Where we studied transverse waves on a taut string in chapter 16. So you have a uniform string that's long and is horizontal and held under tension if you don't disturb it. And then you disturb one end. And let's say you move one end up and down with simple harmonic motion. Then you create what's called a sinusoidal traveling wave that travels down the string. And yes, that was studied a lot in chapter 16. Okay. Okay, so then if I kind of draw some pictures here, if I draw a snapshot, what I call a snapshot graph of this sinusoidal traveling wave in the string, it might look like this. Horizontal x-axis, that's where the string would be resting if I didn't disturb it. And then perpendicular to that will be a y-axis, and that's the direction the strings, pieces of the string will move up and down, not left and right. And let's just say for the sake of argument that my snapshot, it looks like this. I'm not the world's best artist, as you know, okay? And it goes on and on and on to the left and the right, and a snapshot. And that kind of a shape, that's what the actual string would look like if you took a picture of the wave at a particular moment in time. Let's just say for the sake of argument that we took this snapshot at time t equals 0. You can see the way I've drawn it, that it's a sine wave. I mean, it's literally a sine wave. That's what I meant to draw. That's what that's meant to look like. So the wave function, the function that gives you the y displacement of a piece of string at a particular x location at this time. So you have to pick an x location, like right there. And that you have to pick a time, like t equals 0. And you're asking, at that x location and at this time, what's the y displacement of that little piece of string? I want a formula for that. It's called the wave function. It's the function y of x and t. Y is the dependent variable, and there are two independent variables. X, where are you on the x-axis? And t, what is the time? And the formula for this sinusoidal traveling wave which at time 0 clearly is a sine wave the way I drew it, is, well, it'll have some maximum y displacement, y max, sine, because that's a sine curve. And inside the argument of the sine will be a number of things, 2 variables and at least 2 constants. The variables are x and t. There's a constant multiplying the x. It's called the angular wave number, symbol little k. And there's a constant multiplying the t. It's called angular frequency, symbol omega. So there's k times x, leaving some space, and then omega times t. And then between the kx and the omega t is either a plus sign or a minus sign. Which of those signs is it? It depends on which direction the wave is traveling. The wave is the disturbance itself. The wave in this string is traveling either right or left, plus x or minus x. Let's just say, for the sake of argument, there's nothing in my snapshot that would tell you, so you have to be told that the wave is traveling in the plus x direction at some speed v. V then is the speed of the wave, the disturbance that's traveling on the string. If the wave is traveling in the plus x direction, then this needs to be a minus sign, not a plus, a minus. Now, if you were told that the wave is traveling in the negative x direction at speed v, then that sign you would put between the kx and the omega t would be a plus sign. All right, so the v you're talking about here is this, what we call the speed of the wave. And it is determined by properties of the medium. The medium is the thing the wave is traveling on, the thing that has been disturbed. In this case, it's the string. So the speed of the wave is determined entirely by properties of this string, namely 2 properties, which hopefully you remember from the last experiment in lab. The 2 properties are the tension in the string and the mass per unit length, linear mass density, symbol mu. And the formula for the speed of the wave is the square root of the tension in the string divided by its linear mass density. It's these 2 things that determine v. If you want to make a sinusoidal traveling wave and you want to control how fast it travels on the string, those are the 2 things you have to work with: the tension in the string and the mass per unit length. Now, having said that, and I want to emphasize, it's those 2 things, tension and mass per unit length, that physically determine v. It's those things that determine how fast the wave travels. There is another relationship involving v. And it's handy to remember that. And it relates v and omega and k. Those 3 constants, v, omega, angular frequency, k, angular wave number. And it's just a simple combination of the 3, which I always have to figure out by thinking about the units. If I start with a v equals on the left, I know that's meters per second. Then I think I want omega divided by k. Let's see if that works. Omega has units of radians per second. K has units of radian per meter. On the right, the radians cancel, and the units on the right are effectively meter per second. All right, now this is handy to remember. It just says omega, k, and v are related to each other and have to satisfy that. But remember what determines what v is: the tension and the mu. Okay, now that's one of the things you were asked to talk about, v. But there's another, well, I would call it a velocity that we have to contend with. when we're studying a transverse wave on a string. And that is, if I take a little piece of the string, like the little piece right there, that you see there at location X, that's been displaced upward by the amount Y, when I took that snapshot, that little piece of the string that I've painted red there was moving. Not left or right, but up, down, and specifically up. How do I know that? Because the little piece of string that's immediately to the left is what's coming down the pike for this red dotted piece of string. And that little piece of string that's immediately to the left is higher up. So I know that the piece of string that I painted with the red dot when I took that snapshot was moving and moving upward in the plus Y direction. And that's the transverse velocity at that location X, at that time T. So I'll draw it here, pointing up. And that's what your book calls little u. Notice it really doesn't have anything to do with v, the speed of the wave itself going down the string. In this case, v is in the plus x direction. This is completely different velocity. And it's the velocity of a piece of the medium. And it can only be either plus y or minus y in a transverse wave like this. And there may be times when we want to calculate that transverse velocity, symbol u, and we need to be able to do that. Well, it is also a function of the two independent variables x and t, just like the y function is, because you got to tell me, where are you on the x-axis and what's the value of the time? And then I will tell you the transverse velocity of that little piece of string. That's what this formula is going to be. How do we calculate it? Well, this little piece of string is moving along the y direction, and velocity is still rate of change of position, just like in chapter 2, except now it's rate of change of y position because the string is moving parallel to y. So it's the derivative of y with respect to time that's going to give us this transverse velocity. Now there's one more complication. The function y right here is a function of two independent variables, x and t. But I only want the rate of change of y with respect to t, because that's what velocity means. So I want to take the derivative of the y function with respect to t, and I want to treat the other, what would normally be a variable x, as if it were a constant. And when you do that, when you take a function of more than one variable, and this is the whole purpose of multivariable calculus, Math 210, when you take a function of more than one variable, and you want the rate of change of that function with respect to one of those variables, holding the other variables constant, it's called a partial derivative. And the notation is a curly D notation. Curly D of y, of x and t, with respect to t. Curly D. That's the standard notation for what's called a partial derivative. And it really is not, I mean, you can go through all kinds of proofs about what's legitimate way to do this derivative, but it really boils down to the simple fact that you take the derivative of y with respect to t, and everywhere where you see an x, just treat it like the k and the omega, i.e. like constants. So let's see what we get when we do the partial derivative of y with respect to t using this function right here for the y. Note where the t dependence is, it's inside the sign. So I have a sign of a blob, so I have to use the chain rule. The derivative of sine blob is cosine blob times the derivative of the blob. So when I do this partial derivative to get u, I'm going to have, well, there's that y max out front, that's still there. The sine blob becomes cosine blob. And then I multiply by the derivative of the blob with respect to t, treating x and k and omega as constants. Well, then the kx term doesn't survive at all, and the negative omega t just becomes negative omega, multiplying everything else. So I would write that now like this. And now I have a nice function for calculating the transverse velocity for any point on the string. I'm assuming I already know k and omega and y max because they were involved in the y wave function up above. So I already know y max, k, and omega. So you tell me x and t, and I will plug them into this formula and I will tell you u. Make sure your calculator's in radian mode, by the way, when you're taking the sine or the cosine here. In this chapter, the sine and the cosine, their arguments are in radians. Okay, now, does that answer part of the question here? That was the connection between u and v for a sinusoidal traveling wave. Okay, so hearing no complaint, there was also a question about chapter 17. How does temperature affect pressure, B, bulk modulus, inertia, and velocity? Okay, so in chapter 17, we're studying longitudinal waves in a medium, and we call those sound waves for short. Okay. And we spent quite a bit of time, for example, talking about the details of a longitudinal traveling wave in, say, air, a sound wave in air. And one of the things we talked about is how to, or what determines the speed of a longitudinal sound wave or longitudinal traveling wave, i.e. a sound wave in a medium, the V, okay? All right, so a sound wave in a medium. And what you discover is a bit of a pattern between chapters 16 and 17, even though 16 was about transverse waves and 17 is about longitudinal waves. When it comes down to figuring out the V of the wave, there's a pattern. It's given by, first of all, it's determined by properties of the medium. That's true in 16 and 17. It's given by the square root of a fraction. The numerator is a measure of the compressibility, if you like, or the elasticity or the springiness of the medium. In chapter 16, that was the tension of the string. For a fluid, a solid or a liquid, it's something called the adiabatic bulk modulus, symbol capital B. It's a measure of how hard it is to compress the fluid. Air is easy to compress, for example, and has a small adiabatic bulk modulus. Water, on the other hand, is very hard to compress. And most solids, steel, iron, what is also, for example, are also very hard to compress. You can do it, but it's very hard. That's called the adiabatic bulk modulus. And then downstairs is a measure of the inertia of the object. And in this case, it's the volume mass density rho. Okay, so that's what determines the speed of a sound wave in a medium. And the bottom line is both those two things, adiabatic bulk modulus and density, if you study them in materials, are temperature dependent. And so B over rho is temperature dependent. And so what you discover is that the speed of a sound wave in a medium does depend on the temperature of the medium. You don't need to know how the bulk modulus depends on temperature. You don't need to know how the density depends on temperature. We'll learn a little bit about that in Physics 111 next semester. But for now, I'm just telling you one of those material science facts, that bulk modulus and density actually both depend on temperature. Therefore, the V of a sound wave in a medium technically depends on the temperature of the medium. Sound waves in cold air on a cold winter day don't travel as fast as sound waves in warm air. So just be aware of the fact that the speed of a sound wave in a medium does depend on the temperature of the medium. Now, that being said, the most common medium we're going to have is air for sound waves. And we're most likely going to have air at what we call room temperature. Okay. And in that case, if you're talking about air at room temperature, a handy number to remember, although it is in your book, you can look it up, is that the speed of sound in air at room temperature is 343 meters per second. So all I really want you to be aware of here is that what determines the V of a sound wave, those two properties, bulk modulus and volume mass density, and just be aware of the fact that those two things depend on temperature, and therefore so does V. Okay. Now, I have another question that's come up in the chat box. Can we briefly summarize when we have to put our calculators in radian mode as opposed to degree mode? Okay, yeah. Okay, well, it's context dependent. Let's say we're taking sine or cosine. Oh, let's take sine. And of course, as you know, we take the sine of an angle or cosine of an angle. Okay, that's what you do. You take the sine or the cosine or the tangent or secant or cosecant or cotangent of a quantity that we call an angle. Think of right triangle trigonometry. And the confusion comes from the fact that angles can be measured in more than one unit. You can have angles in degrees, or you can have angles in radians. And there are even other units you can come across if you study this stuff long enough. Okay, but let's stick to degrees and radians, that's enough. So you have to know what unit the angle is in. Is it in degrees? Or is it in radians? And that will determine what mode your calculator's in when you take the sine or cosine or tangent. Now you can turn that around and you can say, well, suppose I know that I've got some angle theta and I already know what the sine of it is. This is just some number here, x, and I already know that. Well, as we all know, the way we get the theta then is we take the inverse sine of both sides. So you'd go to your calculator and you'd put inverse sine up. Okay? All right. Now, what mode should you put your calculator in? Degree or radian? It depends on what unit you want for the angle again. Do you want it to be in degrees or do you want it to be in radians? If you want to know the angle in degrees, the calculator in degree mode. If you want to know the angle in radians, have your calculator in radian mode. Now, in chapters pretty much 15, 16, and 17, we had to deal with sines and cosines. And the sines and the cosines had arguments. Let's do the wave function we had up above for a transverse wave on a string. How about that right there? Sine of kx minus omega t. When you are studying oscillations and waves, like this situation, the argument of a sine or a cosine, that's pretty much what you're going to have to deal with. The thing inside the sine or cosine is always assumed to be in radians. The whole thing, that whole argument, your book calls the phase, and it is assumed to be in radians. Okay, so in oscillations and waves, the argument of your sine or cosine is in radians. You can take that as a given. So pretty much in chapters 15, 16, and 17, your calculator should be in radian mode. If it's an older chapter, this could happen, where we had like an inclined plane and I gave you some information and you used Newton's second law to solve for the angle of the incline. There, and you have to do like an inverse sine or an inverse cosine of something as the last step. You're probably just going to want to tell me the angle of the incline in degrees, because that's how we normally tell you the angle of an inclined plane, in degrees. So put your calculator in degree mode when you take the inverse sine or cosine. Okay. All right. So your calculator's mode, degree versus radian, is based on what unit you want for the argument inside there, the theta. In chapters 15, 16, and 17, that argument is assumed to be in radians. Hopefully that was helpful. Basically, in chapters 15 and 16 and 17, calculator in radian mode. Okay, now I've got another question. Next question, this question asks, can we go to problem number 2 on the practice final and talk about that one? So let me do that. I will look that up. I'll read it to you so that we can then do that. Okay, so now we're referring to practice final problem 2. I will read it. A transverse sinusoidal wave is moving along a string in the positive direction of an x-axis with speed v equal to 80.0 meters per second. At the instant t equals 0, the string particle, the little piece of string at x equals 0, has a transverse displacement, y displacement, of y equals 4 centimeters from its equilibrium position, and this part's in italics, is not moving, period. The maximum transverse speed of the string particle at x equals 0 is u max equal to 16 meters per second. The wave function has the form y of x comma t equals y max sine of kx plus or minus omega t plus phi. All right, so we're given a bunch of words, and now here come the questions. First question, what is the frequency f of the wave, including units? Okay, now here's one of those problems where all those words can really make you confused, so you need to draw a sketch. Since I'm told something about the wave at time t equals 0, I'm going to draw my snapshot at time t equals 0. Snapshot of this wave. So I have a horizontal x-axis, and perpendicular to that, I have a y-axis, and the string is being displaced along y direction. It's a transverse sinusoidal wave. And now let me try to sketch this wave at this time 0. They're telling me a good bit of information, but they're telling it to me in code to see if I understand or how much I understand about sinusoidal transverse waves, because they tell me at this moment, t equals 0, the string particle that would be resting at x equals 0, right there, see the red dot? It would be there if there were no wave at all, has been transversely displaced in the y direction by 4 centimeters. So it's somewhere up here. Let's say that's 4 centimeters up. And it's not moving. You know what that tells me? That's the highest that piece of string gets, because it's when it's at its extreme high point that the string is momentarily at rest. So I know that this is the peak of a wave, and that if I draw it for other x's beyond that, it goes down from there. like that. Dot, 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 dot. You see what I'm saying? I had to be able to figure that out from those words that are in italics. Is not moving. That's how I know that it's up at its highest point. That means this displacement right here, the y displacement of that piece of string at that moment is actually y max, the amplitude of the wave. And that the transverse velocity of that piece of string, u, is 0. It was not moving when I took that snapshot, neither up nor down. It was for one instant in time at rest. Okay. Now that's a good bit of information. And that means I know now y max, because I'm told that displacement there is 4 centimeters from equilibrium. So 0.04 meters. That's now the amplitude of that wave. I had to deduce that, but that is what that is. Okay, now I'm ready to do part A. What is the frequency F? Again, this is one of those things where you feel like I have no idea how I'm supposed to get that. But actually, there is a lot of information here. Okay? One of the things you learn when you study transverse sinusoidal waves on a string is that when you calculate the transverse velocity function u, that's that function right there that I was just talking about, u of x and t, the amplitude of that transverse velocity function is that combination right there, omega times y max. And that combination is u max, the amplitude of the transverse velocity. Very handy little relationship. Comes right out of that u function right there. So I'm going to use it now. U max equals omega times y max. That's that little relationship I just circled up above. U max equals omega times y max. Now remember, in part A, they want the frequency F. And I deliberately, by the way, when I wrote that exam, I deliberately put the symbol F in there. I'll read you again what A says. What is the frequency F of the wave, including units? I'm trying to help you there. I'm trying to warn you, don't confuse F with omega. I'll tell you this, I took this problem out of your book, and your book did not put in the F. Or probably didn't, it very likely didn't, and would probably just said, what is the frequency of the wave? Meaning you have to realize they mean F when they say frequency. Don't confuse F with omega. They're not the same. They're related, but they're not the same. In fact, omega is equal to 2 times pi times F. So I can write the U max formula like that, 2 pi F Y max. And I contend that's enough. I can solve for F. I already know Y max, 4 centimeters, 0.04 meters. I will remind you, remember you of course have this in front of you when you're working on the test, you're given U max. I'll write it over here to the side. The maximum transverse speed, 16 meters per second. You're just told that. So all I got to do with this formula is solve for F. F equals U max over 2 times pi times Y max. So here I put in 16 meters per second, and here I put in 0.04 meters. Make sure everything's in SI. And then I go to my calculator, and when I do that, I get 63.67. The unit is per second, which is traditionally called a hertz. And then I round that to 3 sig figs. And I get 63.7 hertz. Okay. I mean, if you're within 1 or 2 of that, I mean 0.1 or 0.2, you're fine. Okay, all right, that's part A. There's a lot of things we can ask about the wave, so it's clearly going to be more than just one thing. Here's the next thing, B. What is the wavelength lambda of the wave, including units? So now we want lambda, the repeat distance. That would be, for example, in my snapshot, the horizontal distance between two successive crests, like that. How am I going to get that? Because I don't have any scale on my picture along X to just read it off the X-axis. Well, I need relationships that I know about sinusoidal waves. This one, the most direct one, is the one that relates wavelength to speed and frequency f. It's that simple little formula. Wavelength in meters equals speed of wave in meters per second over frequency in hertz or per second. And I know all those things on the right-hand side. I'm told the v of the wave, 80 meters per second. And for the frequency, I'll put in my unrounded answer. And I get for the wavelength, 1.257 meters. So if I round that to 3 sig figs, 1.26 meters. And I've given you now the wavelength. So that's that distance lambda in my drawing up there. Now part C. What is the amplitude Y max including units? Well, it's a question because the problem didn't come out outright and say what the amplitude is. I had to deduce it, but I already did deduce it in my talk up above and labeled it, figured it out, that the amplitude of the wave is that displacement of that piece of string that would be at the origin, 0.04 meters. So I just have to write that down. D, what is the angular wave number, K, including units? Here, amongst the many useful formulas for sinusoidal traveling waves, you need to know the relationship between angular wave number K and wavelength lambda. It's that. K equals 2 pi over lambda. Just plug in now. 2 pi, we don't often write it, or we don't always write it because it's not necessary, but there is a radian unit with that 2 pi. And then the lambda, I'll use the unrounded value, 1.257 meters. So I'm going to get a number in radians per meter. And to 3 sig figs, I get 5.00 radian per meter. That's K. E. What is the angular frequency? Angular frequency, omega, including units. Omega. Well, omega is 2 times pi times the frequency, f. And I already figured the frequency out. 2 pi, yes, that's 2 pi radian if you want to be technical. And I usually am. And the frequency is, if I use the unrounded value, 63.67 hertz. Remember, hertz is a per second. So that is radians per second. And that turns out to be, to 3 sig figs, 400 radians per second. Okay. Okay, next. What is the phase angle phi, including units? Okay, now here what you've got to note is we're told up at the beginning of the problem that the wave function, the function y of x comma t, is to be written like this: y max times sine of kx plus or minus omega t plus a phase angle phi. And they are now asking me, what's that phase angle phi? I'm going to answer that by looking at my drawing up above. That's a snapshot of the graph, of the wave at one particular time, t equals 0. And if I look at my wave function at time 0, let's write down what that would look like mathematically. So now I'm looking at the function y of x comma 0. because I'm going to plug in 0 for the t variable. And I'm left with y max sine of kx plus phi, right? I just set t equal to 0. All right, now I need to be able to look at my snapshot drawing of the wave, compare it with this function, and figure out the phi. Now, if my snapshot wave were a simple sine curve, like this, then the phase angle would be 0. It's a simple sine with no shift left or right. The problem is that's not the shape of our curve, right? Our wave. See up there in the red curve? That's not a simple sine. In fact, it's a cosine, isn't it? Right? That's a cosine curve. So what does phi have to be? Here, what does its value have to be in radians so that the sine of kx plus phi is equivalent to y max cosine of kx, just a cosine, because that's what I've got. And this is where all that trig that we wanted you to learn in high school, we're saying, okay, we need to know this. The phi is pi over 2 radians, a quarter of a cycle. That is to say, i.e., sine of kx plus pi over 2 is equal to cosine kx. I can check that with using one of the trig identities called the sum rule for a sine. Sine of one blob plus another blob. And the sine rule, the sum rule for the sine says, you got the sine of two things added together, a plus b. You can write that as sine of a cosine of b plus cosine a sine b. Then use the fact that cosine of pi over 2 is 0, sine of pi over 2 is 1, and the whole thing is now just equal to cosine kx, like I wanted. So that was more kind of deducing from the wave function and then the shape of the snapshot graph that I drew, what the phi has to be. Has to be pi over 2. What else? There's more. G, what is the correct sign, plus or minus in front of the omega? Right here. Which is it, plus or minus? You can't just keep it at both. Any particular wave is one or the other. What's the correct sign for this wave? S-I-G-N. Positive or negative? Here, at this stage, I just recommend you remember, if the wave is traveling in the plus x direction, you will use the minus sign. And if it's traveling in the negative x direction, you use the plus sign. They're opposites. So here it's just a matter of stating. You use the minus sign. So the argument in there is that. That's what's inside the sine function. Okay? So the answer is that right there, the negative sign. And then there's one more part, h. What is the value of y, the transverse displacement, including the units, at x equals 2 meters and t equals 2 seconds? My drawing is a snapshot of the wave at time 0. Now we're taking the time of 2 seconds. So we're letting the clock tick away for 2 seconds. And then we're asking, okay, then we're saying, go out on the x-axis to x equals 2 meters. Well, that'd be somewhere roughly out in here. And the time is 2 seconds. Tell me the y. What's the y displacement right there? All right, well, you can't just look at that picture and guess. There's got to be a way to calculate it. And that's where that wave function comes in. Y of x comma t is y max sine of kx minus omega t plus pi over 2, which you can, using the sum rule for the sine, write as y max times cosine of kx minus omega t. Because sine of blob plus pi over 2 is equal to cosine of blob. So here what I'm wanting to see is, can you just use this formula correctly? So now we're going to plug in for the x 2 meters and the t 2 seconds. And all the other constants, y max and k and omega, we have to plug in their values as well. So y at x equals 2 meters, t equals 2 seconds equals y max, we already wrote that down, 0.04 meters. Notice how I'm writing the units. Cosine, let me use square brackets. K, angular wave number. I already figured that out. So let me write its value. 5 and the unit, radian per meter. Then I multiply the K by X that we were given. We were given an X of 2 meters. There's KX. Then minus omega, we already figured that out. 400 radian per second, and multiply that by the T we were given. 2 seconds, close bracket. Look at units carefully. Per meter cancels meter. Per second cancels second. Notice that this term, the first term has a unit of radian, and the second term has a unit of radian, which is what it should be. The argument of the trig function should be in radians. So your calculator needs to be in radian mode. And now you take, well, you can see what the number is inside the brackets there. 5 times 2 is 10 radians. This is 10 radians. Minus 400 times 2 is 800 radians. So you take 10 minus 800, make sure your calculator's in radian mode, take the cosine of it, and then multiply by 0.04. And I get negative 0.00441 meters. If you want to give that in centimeters, you can just multiply by 100. Negative 0.441 centimeter. Notice it doesn't say I have to give the answer in SI units. You can if you want, or you can do it this way. Or you could even give it in millimeters, just so long as you label the units. Okay? All right, so that's, I think, a good problem to see how well you understand properties of a sinusoidal transverse traveling wave. Anyone have any questions about that problem? Anyone have another question they'd like to ask me?
Professor,
Yes.
you said something about sending us instructions about the automated email.
Yes. I think it's a good point here to talk about how this is going to work, the final. And I am recording this, so even if people aren't here, if they watch, they can get this information. So here's what's going to happen. As I mentioned in class last week, you have a 4-day window available for taking the exam. Tuesday, Wednesday, Thursday, Friday. Basically starting at 12:01 a.m. on Tuesday and going until 11:59 p.m. on Friday. Now that's the window that's available to you. Here's how it will work. I will be sending out to the class, it's going to be automated, at 12:01 a.m. tomorrow morning, an email with an instruction that's going to tell you how to request the exam. It's basically going to boil down to sending me an email with the appropriate words in the subject line. And my email to you at 12:01 a.m. tomorrow morning will tell you what to put in that subject line. So when you are ready, you've got the 4-day window to decide when you want to do it. When you are ready to take the exam, you send me an email. I think you better use your OWU email account just to be safe. And you will put in those appropriate words in the subject line. I will tell you what those are. As long as you put the appropriate words in the subject line of the message, I have programmed Gmail to automatically respond. Again, I don't have to actually be involved. It's all programmed. It will automatically respond and send to you the exam. It'll actually be a link to get the exam. The minute you receive that message, okay, the minute you receive that message, it is assumed you have the exam. At that point, a clock starts because you have 24 hours maximum to email to me your work. Okay? And when you email to me your work as a single PDF, don't forget to sign the beginning of your work, acknowledging you followed the rules. Right? Then you have turned in your final. You have 24 hours once you request the exam. That makes sense? Is that clear?
Yes. Although
Okay.
I have a question.
Yeah.
How long would the exam really take?
Well, that's going to vary by person, right? As I said, it's 8 problems. In the old days, when I gave exams in a classroom, this exam would have had 3 hours. Same test, 3 hours. And no, you wouldn't be able to use your book. I would let you bring a sheet with equations on it, but you would not be able to use your book. So it's a different kind of exam, but in the old days, 3 hours. And if you studied, this is an exam, so you do want to study, you do want to review. Don't think of it as a long homework set. Think of it as an exam, and you need to prepare for exams. If you have prepared for exams, then I have found this in the past, you can do this exam in 3 hours. I'm giving you 24 so that no one will feel rushed. Okay?
Okay.
So don't rush. Take your time. Try to avoid little calculator mistakes or algebra mistakes. And I do recommend you prepare. And by prepare, I mean make sure you can do all the Wiley Plus problems. Make sure you review some of the older material that you may feel a little rusty on. Okay, so that you have an even better understanding of that material. You'll find the second time around when you review material that we have already studied, it will actually make even more sense when you review it. And that will help you, right? The more you understand the content, the more the problems will make sense to you, and the more you will be able to solve them correctly. That's my advice then. So do prepare. I recommend you do prepare, but also budget your time. Figure out a window where you can give yourself enough time. I really don't think it should take you 24 hours. I really, really don't. But I don't want you to feel rushed. So you decide where during those 4 days you want to take, when you want to take your physics exam. But please don't be emailing me Friday at 11 in the evening asking for more time, because you've got plenty of time to figure out when to take it. Any other questions about the exam and the structure of it?
For the final, do you recommend that we like have like, I know in my notes I have like equations. Do you recommend that we write them all in the same like sheet? You think that'd be helpful for us?
It could be. I wouldn't spend a huge amount of time preparing that sheet. If it were the old-fashioned kind of exam in the classroom where you didn't get to use the book and all you did get to have was a sheet of paper like this where you wrote the equations on and the students had to prepare their sheet before the final and then bring it with them and use it. Yeah, you would spend a lot of time preparing that sheet because it's part of your review. Here, maybe what you want to do is just kind of jot down what are the most important concepts in the various chapters, especially the ones we use the most. For example, the constant acceleration equations are introduced in chapter 2. So if you have to look one of those up, you know where to look it up. Newton's second law problems are in chapters 5 and 6. Work and energy problems are in chapters 7 and 8. Linear momentum and collisions with objects moving linearly is chapter 9, and so forth. Okay, so yes, you could spend some time writing down an equation sheet, and that might help you. But mainly, I would recommend know where material is in the book, so that you don't spend a lot of time just scrolling through the various chapters. Wait a minute, where was this formula? Where was this? You know where it is. You're just didn't bother to memorize it, and you need to look it up. Does that make sense?
Yes, thank you.
Sure. Any other questions? Okay, well, I wish everybody good luck on all their finals. I understand it's a very stressful time. I do remember taking finals. But no matter how stressful they feel, you know you are pretty much right at the end. The semester is nearly over and you get a break. You can recharge. We get a long break this time, and I hope everybody and their family is well, is healthy, and you just get a chance to recharge, relax, just do some reading for fun, et cetera, and then you're ready next semester. If it's Physics 111 or whatever classes you're taking, you'll be ready to start in February. I will, of course, be available throughout the week. If there's a question that you want to ask in terms of clarifying on the final, you may do so. If you want to ask me something in terms of explaining, you should ask before the final exam window opens. You know, if you, Professor, can you explain moment arm more to me or something? Otherwise, please just remember, you should be looking for an email that will come in at 12:01 a.m. Eastern Standard Time with the instructions for the final, how to access it. And then don't forget to have it turned in by Friday at 11:59, and that you have 24 hours once you receive it. Okay, well, good luck to everybody and have a good break. And I hope to see you next semester.
Thank you.
You're very
Thank
welcome.
you.
You too.